Dear student, welcome. We are in the series of electronic circuits, and today's lecture based upon the inductors, and we are discussing the two type of inductance. First is the self inductance and second is the mutual inductance. What is the mutual inductance? Mutual inductance produced between the two coils. That is a property of the coil due to which it opposes the change of the current in the another coil. Or we can say we are having a two coil, one is a neighboring coil, then another will change. When the current in the neighboring coil changes, the flux set up in the coil, and because of this the changing flux induced in the coil. Changing flux EMF is induced in the coil, and that is the mutually induced EMF, and the phenomena is known as the mutual inductance. Now we consider that, let us understand the phenomena of the mutual inductance by considering the example as we are having here. You see on the screen that we are having a two coil A and coil B. Coil A connected with the battery as well as the resistance, and above, which is the coil B, connected with the galvanometer. Now the two coils, namely A and B, are placed nearer to each other, and when we switch S is closed. When the switch S is closed, the current flows in the coil. As the current flow in the coil, then it set up the flux phi in the coil A. The flux will produce in the coil A. Now in the coil A, and the EMF is induced in the coil A. Now if the value of the current is changed by varying the value of the resistance R, the flux linking with the coil B also changes because of this changing current. So as this change in the A, because of the mutual inductance, current in the coil B, the changing because of this changing in the A, the flux linking with the B also changes because of the changing current in the coil B. Thus the phenomena of the linking flux of the coil A with the other coil B is called the mutual inductance. Because of this change in the flux because of the another coil, that's why mutually changing takes place, that's why it is called mutual inductance. For determining the mutual inductance between the two coils, the phenomena is expressed as, we can take it as EMF M is equal to M di2 divided by dt, or we can write it as M is equal to EM by di1 by dt. So now EM is equal to, the expression is used when the magnitude of the mutually induced EMF in the coil and the rate of change of the current in the neighboring coil is known. So if EMF 1 volt and di1, current in the one coil, is change in current in the coil A 1 ampere, and then putting this value in the equation 1, then we can get the mutual inductance M 1 Henry. Hence from the above statement, the mutual inductance defined as the two coils are said to have a mutual inductance of a 1 Henry if the EMF of 1 volt is induced in the coil when the current flowing through the other neighboring coil or the secondary coil and is changing the rate of 1 ampere per second. And mutual inductance can also be expressed in another way as EM is equal to M di by dt is equal to d by dt Mi1, and EM that we can define by the number of coils also, N2 d phi by 1 L d phi by dt, which is equal to d by dt N2 phi 1 by 2. So Mi1 is equal to N2 d phi by 1 d phi 1 2, or M is equal to N2 phi 1 2 by I1, that is defined in the Henry. The above expression used when the flux linkage N2 phi 1 2 of the one coil to the current I1. Means we are taking the change in the current in the second coil. So because but it based upon the change in the current pass in the coil 1 flowing through the other coil as known. So value of mutual inductance depends upon the following factors. Number 1 is the number of turns in the secondary or the neighboring coil. Number 2 is the cross sectional area of the inductor, and third is the closeness of the two coils. So the mutual inductance depends upon the three factors. One is number of the coil, number of the turns in the coil. Number 2 is the cross sectional area. Number 3 is the closeness of the two coil. Mutual inductance in the magnetic circuit, we can define it as on a magnetic core, two or more, or then the two coils are wound. The coils are said to be mutually coupled. The current when the passed in any of the coil would around the magnetic coil produces the flux which link all the coils together and also the one in which the current is passed. Hence there will be both the self inductance and the mutual inductance in each of the coil. For this, the best example is the Faraday law of the electromagnetic induction, example of the mutual induction in the transformer, which works on the Faraday law of the electromagnetic induction. And the Faraday law of electromagnetic induction states that the magnitude of the voltage is directly proportional to the rate of change of the flux. Magnitude of the voltage directly proportional to the rate of the change of the flux. That is the Faraday law of electromagnetic induction, which explain the Faraday law of electromagnetic induction. The Faraday law of electromagnetic induction was given in 1930 by the Michael Faraday, who explained the electromagnetic induction, which gives the relationship between the electric voltage and the changing magnetic field. The Faraday law of electromagnetic induction that will explain the here we can explain by the example. We are having to explain the electromagnetic induction. We take the closed circuit. When the current flow, the EMF is induced in it. Therefore, the phenomena in which the EMF is induced in the circuit when the magnetic flux linking with it gives the electromagnetic induction. So that we will define by an example. What is the example? They consider a coil having a large number of the turns to which the galvanometer is connected. You see in this diagram, we take the first case of the electromagnetic induction. Here, when the coil is stationary and the magnet is moving. You see on the left hand side, we are having a electric circuit where the inductors is connected with the galvanometer. On the right hand side, we are having a magnet. So in the first case, we are having the coil is stationary and the magnet is moving. This magnet is moving in the 2 and 1 direction. See carefully on the diagram, there is a mentioned 1 and 2. So first we move away towards the 2 by the number 2 and we just take this magnet nearer to the coil. So when the permanent bar magnet is taken nearer to the coil, that is the position 2, and away from the coil, that is the position 1. As shown in the figure, we can see the deflection takes place in the galvanometer, and this deflection is opposite in both the cases. If it is nearer, then it will be left. If it is right, then it is right. So both the deflection is different. In the second case, we can have the coil is moving and the magnet is stationary. Now the magnet is stationary but the coil is moving as 1 and 2 direction. The bar magnet is kept stationary and the coil is brought nearer to the magnet, that is a position 1, and away towards the magnet, that is a position 2. The deflection will take place in the galvanometer. In both the cases, direction of the needle will opposite. This can be explained as the magnet is brought nearer, the needle will deflect it towards the right. When it is away, then it moves towards the left hand side. Then that is the opposite case when we move the bar magnet right and left, away and the nearer. There is another case, that is the case 3, when the magnet and the bar, when the magnet and the core both are stationary. When the magnet and the core are stationary, there will be no deflection in the coil, regardless how much flux is linked with the coil. So from this, we analyze that The deflection of the galvanometer needle indicates the EMF is induced in the coil because of the magnetic moment. The deflection takes place only when the flux linking with the circuit changes and either the magnet or the coil is in the motion, and because of that the current will generated and EMF is induced, and the deflection will produce in the galvanometer. The direction of the induced EMF in the coil depends upon the direction of the magnetic field. The direction of the induced EMF depends upon the direction of the magnetic field and direction of the motion of the coil. This is the electromagnetic induction, how we can consider. Next important part is the working of the induction motor. Induction motor, we require a motor that works on the principle of the electromagnetic induction, that is the induction motor. Electromagnetic induction is the phenomena in which the electromotive force induced across the electric current when we place it in the rotating magnetic field. So this motor contains the two essential parts. First is the stator and second is the rotor. The stator is stationary part and rotor is the moving part. The stator stationary part, it carries the overlapping winding, while the rotor carries the main or the field winding. The winding of the stator are equally displaced from each other by the angle of 120 and these are closely wound. The induction motor is the single excited motor that is applied only to the one part, that is the stator. The term excitation means the process of inducing the magnetic field on the parts of the motor. It means excitation is produced like the induced magnetic field produced in the motor. So when the three-phase supply is given to the stator, the rotating magnetic field produced in it. As we see in the figure, we consider the rotating magnetic field induced in the rotating magnetic field is induced in the anti-clock direction. The rotating magnetic field has moving polarities. The polarities of the magnetic field vary by concerning the positive and negative half cycle of the supply. The change in the polarity makes the magnetic field rotates. Here you see in the diagram that this is the induction motor. You see that the outside we have the stator, rotator is inside, and the main field is in between between that. Electromagnetic torque is produced here and the rotating magnetic field is there. Three-phase induction, this is a three-phase induction motor, and here AC power supply for a single for the excitation, and the interaction of the rotor and stator takes place in this part, as we see in the right hand side. Conductors of the rotor are stationary. These stationary conductors cut the rotating magnetic field of the stator. Because of the electromagnetic induction, the EMF induced in the motor, this EMF is known as the rotor induced EMF. This is because of the electromagnetic induction phenomena. So the direction of the electromagnetic torque and the rotating magnetic field is the same in this. Hence the rotor starts rotating in the same direction as that of the rotating magnetic field. The speed of the rotator is always less than the rotating magnetic field or the synchronous speed. The rotor tries to run at the speed of the rotor, but it always slips away. Thus the motor never runs at the speed of the rotating magnetic field. This is the reason because of which the induction motor is always as a synchronous motor. So in this induction motor, if the motor never runs with the speed of rotating magnetic field, this is the reason why the induction motor is always a synchronous motor. So why the rotor never runs as a synchronous speed? The speed of the rotor is equal to the synchronous speed. No relative motion occurs between the rotating magnetic field of the stator or the conductors of the rotor. That's why the rotor never runs at the synchronous speed. So EMF is not induced on the conductor, zero current develops on it. Without current, the torque is also not produced in it. So because of the above mentioned reason, the rotor never rotates at the synchronous speed because of the no torque produced. The speed of the rotor is always less than the speed of the rotating magnetic field. So alternatively, the method of the working principle of the induction motor can also be explained as, first we understand by considering the single conductor on the stationary rotor. So thus the conductor cuts the rotating magnetic field of the stator. You see here, rotor is the below and the stator is at above. So rotor, conductor and the rotation field. So the stationary, so we can say that the conductor cuts the rotating magnetic field of the stator. So considering that will be the field according to the Faraday's law of electromagnetic induction, EMF induced in the conductor. The rotor circuit is completed by external resistance or by the end ring. As we see that there is interaction between the rotor and the stator. So the rotor induces the EMF which causes the current in the circuit. So direction of the rotor induces current is opposite that of the rotating magnetic field. The rotor current induced the flux in the rotor. The direction of the rotor flux is same that of the current, rotor current in the circuit. You see here the current is generated, flux is generated in it. So the interaction of the rotor and stator fluxes develops a force that acts on the conductor of the rotor. As there will be the interaction between the rotor and stator, then the flux will generated, and that flux generated the force, and that acts on the conductor of the rotor. The force acts tangentially on the rotor and hence the induced torque will produce. This torque pushes the conductor of the rotor, thus the rotor starts moving in the direction of the rotating magnetic field. The rotor starts moving without any additional excitation system because of the reason of the motor is called the self-starting motor. The rotor starts moving without any additional excitation system because of the torque produced on it. So that will be the self-starting motor. As the operation of the motor depends upon the voltage induced on the rotor, so it is called the induction motor. So here you see in the diagram, that is the rotation field. What are the difference between the capacitor and inductor? As we are discussing, that inductor is useful, but how it is different from the capacitor. So capacitor and inductors are considerably used in the electronic circuit and are considerably various factor, like they can be differentiated by using the various factors like the calculation of the storage energy, flow of the current, behavior in both the AC and DC circuit, relationship between the voltage, current and its unit, type of inductors, capacitor, the resistance changes and the application. There are many ways of there are many forms how they can be different from each other. So first we discuss the definition, that how the capacitor and inductor difference. The capacitor stores the energy in the form of electric field. But apart from this, the inductor stores the energy in the form of the magnetic field. Calculation of the energy, if we take the energy stored is calculated in terms of the voltage, but here in the inductor that is in terms of the current. So this is the difference between the capacitor and the inductor. If we talk about the flow of current, there is no flow of the current through the capacitor plates, but inductors current flows through the coil, and that produces the magnetic field, that generate the induced EMF. Then on the basis of the DC circuit, behavior of DC circuit, capacitor acts as an insulator for the DC circuit. Apart from this, the inductor acts as a conductor for the DC circuit. A relationship between the voltage and current, in the AC circuit the current leads the voltage by the 90 degree, but here in the inductor the AC circuit current lags voltage by the 90 degree. The difference in the capacitor, it leads the voltage up to the 90 degree, but here the current lags the voltage by the 90 degree. As in the behavior of the current in the DC circuit, when the capacitor is added in the series with the resistance, the current initially becomes high, but later it falls to the zero. But here in this case, when the inductor is added in the series with the resistors, the value of the current is small, and afterwards it increases with the time. In that case, in the capacitor rate will fall 0, but in the inductor it will be high. The capacitor and inductors both are passive components of an electrical circuit, and the capacitor consists of the two metallic plates or the conductors which are separated by the dielectric medium. An electric field set up because of the potential difference between the two conductors, or we can say between the two plates, while the inductor is a type of coil which stores the energy in the form of the magnetic flux, and that is made by the coil. And when electric current is passed through the coil, voltage is developed across the coil due to the change in the magnetic field. What are the application of the inductors? Like resistors and capacitor, inductors are also passive elements which are used to store the electric energy in the form of the magnetic field. Simply, inductor is a wire or a coil of a good electric conducting materials with a few turns, twist in it. It is in the form of the round shape. They will produce a magnetic flux field around them by flow of an alternating current through it, and ideal inductor has no inductive reactance, so it acts as a short circuit. In practical, every inductor has some resistance initially when we call as the inductive reactance. It measures in the ohms. When the inductive reactance of the coil is very high, then the circuit acts as an open circuit, allows the maximum current through it. Inductance is a phenomena of the inductor that opposes the flow of the current in the circuit by generating the back EMF, and that is measured in the Henry. Inductors are many types like air and iron coil. There are the different types and many more. Because of the requirement, inductors have the application in the electric transmission, like inductors in the tuned circuits. We use the inductor in the tuned circuit. You see here, the inductor is connected with the capacitor. The two terminals, one in the series and another is the parallel. Inductors are used in the tuning circuits which are used to select the desired frequency. In the tuned circuit, we have capacitor connected with it, and either in the parallel or in the series, the frequency of the tuning circuit at which the capacitive resistance is equal to the inductive resistance, when Xc is equal to XL, is called the resonant frequency. The series resonance circuit is used for many electronic circuits like television, radio circuits, radio tuning circuits, and the filters to vary the frequency and selecting the various frequency channels. So, capacitor with the inductors can be used to tune the circuit. We produce the inductive sensor by using the inductors. Inductors are used in the proximity sensors which work as a principle of the inductance. We know the inductance phenomena. Then the magnetic field produced in the coil which opposes the flow of the current. Thus the inductance will restrict the current flow and reduce the circuit performance. The better performance we need to amplify the current in the circuit. So we use the proximity sensors to find out the level of the amplification factor at which we need to amplify the current. In the manufacture and designing of the sensor, twisting the wire into the tight coil that will be work as a inductor. There will be the four components of the inductive proximity sensor. They are an inductor or coil, oscillator, detection circuit, and the output circuit. So inductive proximity sensors is a fluctuating magnetic field in generating the oscillator and winding the coil which locates in the sensor face. Here see, this is the inductive sensor, and when the object move in the field of the inductive proximity area of the detection, eddy current will build up and the material will reduce the inductive sensor's magnetic field. Another important application is the energy storage devices, and it is used to store the energy and produce the induction motor using the inductors. This inductor is also used in the transformer, which is the basic and important and the popular application of the inductors. By combining the inductors of the shared magnetic field, we can design the transformer. Transformer is the basic and the fundamental component of the power transmission system. And inductive filters we can prepare by using the inductors. So up to now, chokes, that is very important, that we discussed that we have a fluorescent tube in our houses. The chokes is also prepared by this inductors. We produce the ferrite beds by this inductor. Relays we can produce by this inductors. Thank you very much.